Hey everyone, welcome back. Today we're going to be diving deep,
Yeah.
into the world of electrical circuits.
Oh, fun.
Yeah. Now I know what you're thinking.
It does sound pretty
Circuit,
famous.
a little dry, right? But trust me, we're going to unpack some really interesting stuff from this mechatronics textbook chapter you sent over.
Yeah. It's
Uh,
whether you're
Tinkering with electronics or just curious about how your gadgets work or you just, love learning new things.
Mhm.
This deep dive is for you.
You know what I think is so fascinating about circuits is that they're like the hidden language of our modern world.
Okay, I'm intrigued. So before we get ahead of ourselves, let's start with the absolute basics. What exactly is an electrical circuit?
At its core, a circuit is a closed loop that allows electricity to flow. Think of it like a system of pipes carrying water.
Okay.
The pipes are like the wires. The water is like the flow of electrons, which we call current. And the pressure pushing the water is like the voltage.
So the higher the voltage, the stronger the push on those electrons, right?
Yeah. Exactly. And just like you need a pump to create water pressure, you need a source like a battery or generator to provide voltage in a circuit. And that flow of electrons, that current is what powers, all the amazing things in our devices, the load.
Hold on. I've always been a bit confused about this whole positive charge flow thing. Isn't it actually the electrons which are negatively charged that are moving?
Ah, that's a great question. It actually goes back to Benjamin Franklin.
Oh.
He made a guess about the direction of charge flow, and unfortunately, he got it wrong.
Oh no.
But the convention stuck. So even though we talk about positive charge flow, it's really those negatively charged electrons doing the work.
So we're stuck with Ben Franklin's little oopsie.
Ah.
Okay, well that makes a bit more sense now, but what about different types of current? I've heard of direct current DC and alternating current AC, but what's the difference?
Think of batteries for DC. They provide a steady one-way flow of current, like a river flowing in one direction. AC, on the other hand, is like the current you get from your wall outlets. It changes direction constantly, like waves in the ocean.
I'm starting to see how these analogies really help understand the concepts. So now that we've got the basics of current and voltage, let's talk about the components that make up these circuits. The reading you sent mentioned the big three passive components. What are they and why are they so important?
The big three are resistors, capacitors, and inductors, the fundamental building blocks of just about every electronic device you can imagine. They each interact with electrical energy in their own unique way.
Let's break those down one by one, starting with resistors. What's their role in a circuit?
Resistors are the energy dissipators of the circuit world. They control the flow of current and convert electrical energy into heat. Think of them like the brakes in a car controlling the speed.
Okay, that makes sense. And I remember from high school physics something called Ohm's law. Does that apply to resistors?
Absolutely. Ohm's law, V equals IR, tells us the relationship between voltage V, current I, and resistance R. It means that for a given voltage, the higher the resistance, the lower the current will be.
So resistors are basically the traffic cops of a circuit controlling the flow of electrons.
Precisely. And here's a fun fact about real-world resistors. They aren't perfectly linear. Their resistance can change with temperature, which can be important to consider in certain applications. Also, have you ever noticed those colorful bands on resistors?
Yeah, I always wondered what those were about.
They actually tell you the resistor's value. It's like a secret code, and there's even a mnemonic to help you remember the color code. It's surprisingly useful when you're trying to identify a resistor in a circuit.
Whoa, that's way cooler than I expected. I'm gonna have to look up that mnemonic. Okay, so we've tackled resistors. What about capacitors? They sound a bit more mysterious.
Capacitors are fascinating components that store energy in electric fields. Think of them like tiny rechargeable batteries.
Wait, so they actually store energy. How do they do that?
It has to do with charge separation. A capacitor is basically two conductive plates separated by an insulator. When voltage is applied, charges build up on the plates, creating an electric field that stores energy.
Interesting. The reading mentioned something about capacitors not being able to change voltage instantly.
Hmm.
Why is that, and why is it important?
That's a key property of capacitors and makes them super useful in timing circuits. Think of it like filling a bucket with water. It takes time to fill and empty, just like it takes time for a capacitor to charge and discharge. This ability to control the timing of voltage changes is crucial in many electronic circuits.
So it's like a built-in delay mechanism. That makes sense. Are there different types of capacitors?
Yes, there are many types, each with its own characteristics and applications. Electrolytic capacitors are particularly common, but they have a quirk. They're polarized, meaning you have to connect them the right way. Hook them up backward and they can literally pop.
Yikes, a mini explosion. Good to know. I'll make sure I pay attention to those plus and minus signs. Okay, last but not least, we have inductors. What's their specialty?
Inductors are the masters of storing energy in magnetic fields. They typically look like a simple coil of wire.
So wrapping a wire around a nail and connecting it to a battery would create an inductor.
You got it. The current flowing through the coil creates a magnetic field which stores energy. And the fascinating thing about inductors is that they resist changes in current.
What do you mean by resist changes in current?
Think of it like inertia. A heavy object is harder to get moving and harder to stop once it's in motion. Similarly, an inductor tries to maintain a steady current flow. This property makes them essential in things like motors and solenoids where you can't instantly start or stop the current.
So resistors dissipate energy capacitors stored in electric fields, and inductors stored in magnetic fields. It's amazing how these simple components each have their own unique way of interacting with electricity.
And that's just the tip of the iceberg. Understanding these components and their properties is the first step to understanding the incredible diversity and complexity of the circuits that power our world.
This is way more interesting than I initially thought. But before we move on, I want to make sure I've got this straight. We've talked about the flow of electrons, different types of current, and the big three passive components, resistors, capacitors, and inductors. Did I miss anything?
You've got the fundamentals down. But to really understand how circuits work, we need to talk about the sources of energy that drive them.
Okay, so let's power up and explore those sources. What do we need to know about them?
Welcome back to a deep dive into electrical circuits.
So far, we've covered the fundamental components like resistors, capacitors, and inductors. I like to think of them as the nouns of the circuit world. But now I'm really curious about how these components interact with each other. What are the verbs that make a circuit come alive?
Excellent analogy. To understand how these components work together, we need to understand the rules of the road for electrical circuits. And that brings us to a couple of fundamental laws: Kirchhoff's current law and Kirchhoff's voltage law.
Okay, hit me with these laws. I'm ready to learn the traffic rules of the electron highway.
First up, we have Kirchhoff's current law, often shortened to KCL. It states that the total current flowing into any junction in a circuit must be equal to the total current flowing out of that junction.
So it's like a busy intersection. What flows in must flow out. No electrons suddenly disappear or magically appear out of thin air.
Precisely. No electrons get lost in the traffic jam. This law is incredibly useful for analyzing how current flows through complex circuits with multiple paths.
It makes sense. What about Kirchhoff's voltage law?
Kirchhoff's voltage law, or KVL, is all about energy conservation. It states that the sum of all the voltage drops around any closed loop in a circuit must be equal to zero.
Okay, I need a visual for this one.
Imagine you're hiking on a mountain trail. You start and end at the same point, so even though you might climb uphill and then descend, your total change in elevation is zero.
Ah, I see. So KVL is saying that as you travel around a circuit loop, the voltage might rise and fall, but it always ends up back where it started.
Yeah.
The energy is conserved.
Exactly. These two laws, KCL and KVL, are the foundation of circuit analysis. They allow us to predict how a circuit will behave and to design circuits that meet specific needs.
This is starting to feel like a superpower, being able to predict how electrons will flow. But how do we actually measure what's happening inside a circuit? We need some tools, right?
You got it. And that's where voltmeters and ammeters come in. A voltmeter measures the voltage difference between 2 points in a circuit, and an ammeter measures the current flowing through a particular path.
So if I wanted to measure the voltage across a resistor, I would connect the voltmeter leads to each side of the resistor.
That's right. You're essentially measuring the electrical pressure difference across the resistor. To measure the current flowing through the resistor, you'd need to insert the ammeter into the circuit so the current flows through it.
So it's like cutting a section of the pipe and putting a flow meter in line to measure the water current. Makes sense. But the reading mentions something about impedance matching being important when making measurements. What's that all about?
That's a great point, and gets into some of the practical considerations of working with circuits. Real-world measurement instruments aren't perfect. They have their own internal resistance.
Wait, so the act of measuring something can actually change the circuit's behavior?
Exactly. If you're not careful, the measurement instrument itself can affect the very thing you're trying to measure. It's like using a heavy-duty truck scale to weigh a delicate butterfly. The scale itself might crush the butterfly.
So how do we avoid these butterfly crushing scenarios when we're making measurements?
That's where understanding impedance matching comes in. Impedance is like a combination of resistance, capacitance, and inductance all rolled into one. When making a measurement, you want to make sure the measurement instrument has a much higher impedance than the circuit you're measuring.
So a high impedance voltmeter wouldn't draw much current from the circuit, so it wouldn't significantly affect the voltage you're trying to measure.
Precisely. High-impedance instruments are like stealthy observers barely disturbing the circuit they're monitoring.
This is fascinating. I'm starting to appreciate all these subtle details that come into play. Are there any other practical considerations we should keep in mind when working with circuits?
Well, noise and interference are always lurking, ready to mess up our measurements. Think of it like trying to have a conversation in a noisy room. It can be difficult to hear what's being said.
So how do we filter out the noise in our circuits and get accurate readings?
There are a few tricks of the trade. Using shielded cables to protect the signals, making sure everything is properly grounded, and even using filters to eliminate specific frequencies of noise can all help.
Okay, so we've learned how to measure what's happening in a circuit and how to do it without causing any unintended disruptions. But before we get to actually building circuits, I remember the reading mentioned something about electrical safety.
Absolutely. It's crucial to remember that electricity can be dangerous if not handled properly. You always want to make sure you're working with properly insulated tools and circuits, and you should never work on live circuits.
Right. Safety first. And grounding is super
Sure.
important too, right?
You got it. Grounding is like providing a safe path for any stray current to flow back to the earth instead of through you. It protects both you and your circuits.
Okay, now that we've got the safety briefing out of the way, let's talk about actually building circuits. I imagine there's a whole art to assembling these components and making them work together.
You're absolutely right. It's a bit like baking a cake following the recipe. The circuit diagram is important, but experience and technique play a huge role in getting a good result.
So what are some tips for us novice circuit bakers? What ingredients and tools do we need to get started?
Well, first things first, a clean and organized workspace is essential. Keep your components neatly organized and make sure you have the right tools like wire strippers, pliers, and a soldering iron if you're working with through-hole components.
And what about breadboards? Aren't those helpful for prototyping circuits before you make things permanent?
Breadboards are an absolute lifesaver. They let you connect components without soldering so you can easily experiment and test your circuit before committing to a more permanent design.
So they're like the rough draft of the circuit world. Once you're happy with the design, what's the next step?
For a more permanent circuit, you'll typically use a printed circuit board or PCB. These boards have pre-etched copper tracks that act as the wires connecting your components in a neat and organized way. And that's where soldering comes in.
Soldering is the key skill for attaching components to a PCB, right? I've seen people do it, but I've never tried it myself. It looks kind of like a tiny welding torch.
It's similar to welding in that you're using heat to melt a metal alloy, solder, to create a strong electrical connection. It takes a bit of practice to master, but there are tons of great tutorials available online to get you started.
I remember the reading mentioned something called flux. What's the role of flux in soldering?
Flux is like a cleaning agent that helps the solder flow smoothly and prevents oxidation. It's crucial for getting a clean, reliable solder joint. Think of it like adding oil to a pan before cooking it. Helps prevent things from sticking and burning.
Okay, so we've covered building circuits, but what about when things go wrong? I imagine troubleshooting can be a real headache. Where do you even begin when a circuit isn't behaving the way you expect?
Troubleshooting is a mix of logical thinking, careful observation, and sometimes a little bit of intuition. A good place to start is by double-checking all your connections. Make sure everything is connected as shown in the circuit diagram and look for any loose wires or cold solder joints.
Right? Make sure all the rows on our electron highway are clear and connected. And what about using a multimeter for troubleshooting?
A multimeter is your best friend when it comes to troubleshooting. You can use it to check for continuity, making sure there's a complete path for electricity to flow. You can also use it to measure voltages and currents at various points in the circuit to see if they match what you expect based on your calculations.
It's like having a detective's toolkit to track down the source of the problem. Are there any other common pitfalls we should be aware of?
Don't forget about the power supply. Sometimes the problem is as simple as a dead battery or a loose power connection. It's always worth checking the obvious things first before diving into more complex troubleshooting.
Okay, so we've covered a lot of ground today, from the fundamental laws of circuits to the practicalities of building and troubleshooting them. I'm feeling much more confident in my understanding, but I'm also realizing there's so much more to learn.
You're absolutely right. There's a whole world of fascinating concepts and applications built upon these fundamentals. But before we wrap up this part of our deep dive, I want to emphasize that even seemingly simple circuits can do some pretty incredible things.
Okay, I'm all ears. What kind of magic can we create with these circuits? Welcome back to the final part of our electrical circuit deep dive. It's amazing how much we've covered already, from the basic laws and components to building and troubleshooting circuits. I'm feeling pretty electrically enlightened, if you know what I mean.
Huh.
But I'm even more excited to hear about what we can actually do with all this knowledge.
What's truly remarkable is how these seemingly simple circuits form the basis for so many incredible technologies. Let's start by talking about signal conditioning, the process of taking real-world signals like temperature, light, or sound, and converting them into electrical signals that we can process and use.
So it's like translating the language of the physical world into the language of electronics.
Exactly. Think about a microphone, for example. It takes sound waves, which are variations in air pressure, and converts them into electrical signals that we can amplify, record, and manipulate.
Or like a temperature sensor in the thermostat, turning heat into an electrical signal that the thermostat can use to control the temperature in a room.
Precisely. There are countless examples of signal conditioning happening all around us: pressure sensors in car tires, light sensors in cameras, even the touch screen on your smartphone. They all rely on circuits to convert physical phenomena into electrical signals that our devices can understand.
It's like having a universal translator for the physical world.
Mhm.
And once you have these electrical signals, what kind of cool things can you do with them?
Well, one essential application is filtering. And no, I'm not talking about those Instagram filters that make your selfies look better.
Ha,
In electronics, filters are circuits that selectively allow certain frequencies of electrical signals to pass through while blocking others.
so it's like a gatekeeper that only lets certain VIPs into the electronic party.
That's a great way to put it. Think about noise-canceling headphones. They use filters to block out unwanted background noise while letting you hear the music clearly. Or, in radio communication, filters are used to tune in to a specific radio station while blocking out all the other stations on different frequencies.
Okay, filters make sense.
Yeah.
But I've also heard a lot about digitizing signals. What does that mean? And why is it so important in our digital world?
Digitization is the process of converting an analog signal, which is continuous and can have any value, into a digital signal, which is discrete and represented by a series of ones and zeros.
So it's like turning a smooth curve into a series of steps, like creating a digital representation of a real-world signal.
A perfect analogy. Think about listening to music on a vinyl record versus streaming it online. The vinyl record stores the music as an analog signal, a continuous groove that the needle follows. But when you stream music, it's been digitized, converted into a series of ones and zeros that can be stored, transmitted, and played back by your computer or smartphone.
Oh, that makes sense. And digital signals are much more robust and easier to manipulate than analog signals, right?
Exactly. Digital signals are less susceptible to noise and interference, and they can be easily copied and transmitted without losing quality. That's why our computers, smartphones, the internet, they all rely on digital signals.
It's incredible to think that all this complex digital technology is ultimately built upon the simple principles of electrical circuits that we've been discussing. It's like these circuits are the unsung heroes of the digital age.
Couldn't have said it better myself. And the key components that make this analog to digital and digital to analog conversion possible are ADCs and DACs, analog to digital converters, and digital to analog converters.
So ADCs take analog signals from the real world, like the sound from a microphone, and turn them into digital data that a computer can process. And DACs do the reverse, taking digital data and turning it back into analog signals that can drive things like speakers or motors.
You got it. These converters are the bridges between the analog and digital worlds, and they're essential for all sorts of modern electronics.
Wow, this is truly mind-blowing. We've gone from the basic concepts of voltage and current to understanding how circuits can be used to sense, filter, and even digitize the world around us. It's making me realize just how much these circuits impact our everyday lives in ways we often don't even realize.
It's a testament to the power of human ingenuity to take these fundamental principles of nature and create such incredible technologies.
Well, I have to say this deep dive has been electrifying. I'm feeling inspired to learn more and maybe even try building some circuits of my own.
That's fantastic. Remember, understanding these basic components and principles is like learning the alphabet of electronics. With this foundation, you can start to decipher the incredible complexity of the circuits that power our modern world.
Well, you've certainly sparked my curiosity. Thanks for guiding me through this fascinating world. Until next time, keep exploring and stay curious.